So, hello everyone. Yes, my name is Eleftherios Meletis, a PhD candidate in the University of Thessaly in Greece. And I have to admit I'm very excited and super happy to be present in this first symposium here on tick-borne diseases in Serbia. I wish first of many. And here in my talk I would like to present a development of Bayesian method, a Bayesian model that could be used to utilize the use of Scott-Lecoq's tick indices in order to determine the risk profile for a patient who developed Lyme borreliosis. So if I were to start, I would like to dive into Lyme borreliosis, but I think that the whole audience here is aware of Lyme borreliosis, but as a zoonotic disease is considered one of the most common tick-borne diseases in the North Hemisphere that is caused by the pathogenic parasite within Borrelia burgdorferi, I way to say it correctly, and the disease is transmitted to humans through the bite of infected ticks. And as we can see, the tick vector for Lyme borreliosis in Europe is Ixodes ricinus. And I have added a map that I have seen also in the previous presentations. That this map is about the distribution of the tick that is responsible for the Lyme borreliosis in Europe. That is a map that was generated from the VectorNet 2, I think, coined a synergy between EFSA and ECDC, and we can see that there is a distribution of the tick around Europe. I see that the tick is considered present in the majority of the European countries, and we can see that in the up here, we can see the not red, in Iceland, we can see that the tick is considered newly introduced. So regarding the Balkans, because we are in a Balkan symposium, we can see that either the data here are unknown or the data are not reported. You can see that in the case of Greece and in Serbia, I think the data are not reported. That is common to what have been previously displayed in the other presentations. Of course, some of the symptoms in the humans include the fever, headache, and fatigue, and a skin rash. I think that's more of the information that is widely known. So regarding diagnosing Lyme borreliosis, that I think is considered a challenge because currently diagnostic or xenodiagnostic gold standard for predicting the risk of developing Lyme borreliosis does not exist. Furthermore, it is expected that a large number of tick-infected patients that will not develop Lyme borreliosis. So usually a wait and watch approach is recommended. However, over the last years, I think that a low-budget method assessing the feeding time of the tick has been improved and has been refined using mostly animal models. The ultimate goal is to use this low-budget method, if we were to call, in order to use it as a xenodiagnostic clinical method that can be used to identify the high-risk patients that can be later referred for additional medical attention. And when I say tick feeding time, the tick feeding time can be assessed usually using two metrics that have been reported in the literature that are estimated by the tick measurement and are the Scotland and the Coxal index. Okay, so now moving to the Bayesian part, that our aim here was to evaluate both the Scotland and the Coxal indices, and also to estimate the optimal threshold for these values for the Scotland and the Coxal index that can be used later on to determine or to discriminate the risk profile for a patient to develop Lyme borreliosis. Our approach was implemented in a Bayesian letter class framework, a framework that is based on the Thomas-Bayes theorem. I think maybe you have heard the Bayes theorem. Is a type of framework that is gaining more and more application over the last years because Bayesian statistics have the advantage of combining both information that are already included in the data, that is the evidence we can see the distribution, the yellow distribution, but also have the advantage that we can incorporate extra information that may not be acquired in the data. This is in the form of our prior belief that we may have. So in a way, we can have our posterior, our ultimate, the ending distribution that can be a combination or a weighted average from the information we may have from the data or any extra information that may not be acquired in the data. Now, the novelty of our approach is that the diagnostic evaluation or the threshold evaluation of the Scottal and the coxal indexes is based on the continuous output of each method. So basically, we do not consider the Scottal and coxal index as positive or negative, high or low. We use the continuous measurement, the estimate we have from the tick. And also the test evaluation or the threshold estimation is performed at the rate of the cutoff values, so we do not use pre-specified cutoff values. However, given the range of the values we observe from the ticks, we perform the test evaluation in that whole range. And based on the information we get, we can select the optimal cutoff value that usually is the one that is suggested to use in order to discriminate high and low risk patients for developing Lyme borreliosis. The second novelty is to say that in our data set, the individual observation was considered the tick and the patient pair. So in a way, we have an individual observation where we can have a patient and a tick that was removed from this patient. So basically, in that pair, in that individual observations, we can consider that 4 methods have been applied or estimated. The Scottal and the coxal index, they were estimated, so we have the continuous output for these 2 markers, let's say. We have the PCR testing of the tick, and the patient later on was clinically examined. So in a way, in our case, we can say that a patient is expected to develop disease, as evident by the clinical examination, given that he got infested by a tick that carried Borrelia. That's information we may have from the PCR, long enough to transmit the bacteria to the patient. The long enough is depending on the feeding time that can be measured by the Scottal and the coxal indices. So in our case study, that is Serbia, finally we had 521 observations, so we had 521 pairs of ticks and patients where the tick was removed. And you can see that we have we have recorded the continuous, on a continuous scale the Scottal and the coxal index. We have the PCR test result, either if it's positive or negative. We had the clinical examination of the patient if he's positive or negative, so if he has developed disease or not developed disease. And also we have recorded the tick phase, if the tick was a nymph or an adult. Because we expect that different feeding time threshold to have between nymphs and adults. So we are evaluating Scottal and coxal indices. So we want to find a threshold for the Scottal and a threshold for the coxal, but this threshold will be different if the tick is a nymph or if the tick is an adult. Some general descriptive statistics. Okay, you can see that, for example, we have here the scatter plot of the Scottal index on the x-axis and the coxal index on the y-axis. And you can see that the red dots are the ticks that were tested negative by PCR, while the positive ones are the blue ones. So overall, in both nymphs and adults, we have around 44 PCR positive ticks, where 38 of them were at the nymph stage and 60 of them were at the adult stage. Apart from this plot, we can see that we can consider that there is a positive correlation. So, as it makes sense, both as the Scottal index increases, we expect also the coxal index to increase. So this is for the nymph ticks. This is for the adult ticks. So again, we have the same thing where we can see that the scatter plot of Scottal index and coxal index grouped by the PCR test result. And if we were to have the same scatter plot, but now grouped by the clinical examination, we expect 9 patients out of the 367 where a tick at the nymph stage was removed to be clinically diagnosed with Lyme borreliosis, while only 2 of them out of the 154 adult ticks that were removed, patients developed Lyme borreliosis. So overall, so this is again the 2 patients in the adult ticks. So we have one here and one here, if you can see. So overall, the apparent prevalence, so what we observed, the percentage of patients that were diagnosed with by clinical examination to be Lyme borreliosis positive is around 3%. That is something that agrees with the current literature that reports the incidence rate for Lyme borreliosis in Serbia. Apart from that, from the scatter plots, we cannot estimate, we cannot see a pattern to see where should we place the threshold in order to discriminate high and low risk patients for developing Lyme borreliosis. So in that way, a Bayesian latent class model has been developed from this, for this approach. And generally, there are two significant things in a Bayesian latent class model. The term latent refers to the infectious status, and it means that it's something unknown. Generally, latent class models are built in a situation where you do not have a gold standard, as in this case, so you expect some of the applied methods to produce some false positive or some false negative results. Of course, depending on how well the method performs, you may have more or less false outcomes. So the true infectious status, what is measured is unknown, is hidden. And a very important step in this type of methods is to have a clear definition of what you are measuring. And this is given by the tests you apply, by the methods you have applied in individual observation. So as we explained in the previous slide, here our definition of infectious status was that a patient is expected to develop disease that is measured by the clinical examination of the patient, given that he got infested by a tick that carried the Borrelia that is evident by the PCR that is applied to the tick, as long as the tick infested long enough to transmit bacteria. That is something that is measured by the coxal and the Scottal index. Of course, we assume the absence of a gold or a perfect test, so we do not assume that all of the methods have 100% sensitivity and 100% specificity. And the outcome, the desired outcome, is to have a test evaluation of these methods, mainly here in this scenario of the Scottal and the coxal index, that also as part of the test evaluation is to have the threshold determination, to find which cutoff is the one that is optimal, not to discriminate between high and low profile of patients' potential to develop Lyme borreliosis. So usually when we have continuous test outputs, this is done by constructing a receiver operating characteristic curve. That is basically a plot where on the x-axis we have the true positive rate, while on the y-axis we have the false positive rate for all possible cutoffs. And the metrics that are used is again the sensitivity and specificity, but now it's just that we estimate sensitivity and specificity at a range of cutoff values. So we start saying what would be the sensitivity and specificity if we have a cutoff value at 0. Then we start going by 0.1, 0.2, 0.3. So at each cutoff value, we estimate the sensitivity and the specificity. And we use the value that maximizes the sum of sensitivity and specificity in order to find the optimal cutoff. If I were to be more clear, so we may have on the bottom left, the distribution of the negatives and the positive ones. We see that these two distributions do not have a great overlap. There is a small overlap. So we expect that the receiver operating characteristic to have a big sum of sensitivity and specificity, so yielding the upper left ROC curve, you can see that is close to the upper left corner. As we move to the right, in the middle of the graph, we see that this overlap between two distributions becomes even larger. So we expect that this biomarker to lose some of this discriminatory ability. Because if you were to test an individual that belongs in the overlap, you are not sure if this one comes from the infected or from the healthy group. So this method loses some of its discriminatory ability. And of course, things get even worse when we go to the third column, where we can see that there is a great overlap between the two distributions, and that basically this biomarker is useless because it does not give any information on the discriminatory ability of this method. So in our case, our main model usually consists of having 4 tests applied. These are the Scottal and the coxal index measured on the continuous scale. The PCR, again, measured on the dichotomous scale, positive or negative on the tick, and the clinical examination that was performed on the patient from where the tick was removed. So again, clinical examination is a positive or negative one. So we have 2 continuous and 2 dichotomous tests. We split our population based on the tick phase, so we have 2 subpopulations, one from nymphs and one from adults, because we expect, as we said before, the test characteristics of Scottal and coxal index to differ between nymphs and adults. And yeah, we thought that given the prevalence, we thought that the two subpopulations share the same prevalence estimate. We don't expect the prevalence of Lyme borreliosis to differ between patients either got infected from nymphs or from adults. Given that we saw the scatter plot in the beginning, we accounted for a potential correlation between scrotal and coxal index, because as we've seen, when scrotal index increases, so does the value of the coxal index increases, so we accounted for a correlation. We assumed for the scrotal and coxal index metrics to range between subpopulations. And some of you may be familiar with this type of models. Usually when we have the test interpretation on a continuous scale, we have the applied normal mixture models. However, the other novelty of this method is that the optimal cutoff estimation was based on the posterior positive probability values. So we do not have to take into account the assumption of normality of the distributions. And we assume that the PCR in the clinical examination, the characteristics that the test performs the same across the two subpopulations. And the determination of the optimal cutoff value, the optimal cutoff value was the value that maximized the UDEX index. So as I've said before, for each cutoff value, we get an estimate of the sensitivity and specificity, and we use the UDEX index that basically sums the sensitivity and specificity. So we said that the optimal cutoff value is the one that maximizes the sum of the sensitivity and specificity. So if I were to see some of the results now for this, for the main model, if we were to check for the scrotal index, for nymphs, you can see that on the upper, on the first row at the top, we see the sum of sensitivity and specificity. How well does it behave? On the second row, we see the sensitivity only. On the last row, we see the specificity. So the central line, the line of 3.1, indicates that the cutoff point, the optimal cutoff point that maximizes the sum of sensitivity and specificity is for nymphs, is the scrotal index of 3.1. And we have a range of 2.7 and 3.5 as a confidence interval range around this value. And if we were to have for adults, we expect that a decrease in the cutoff, in the optimal cutoff for dichotomizing patients with low and high risk of developing Lyme borreliosis, and as expected, we have a lower value for the cutoff in adults. You may see that, as evident, we get very high estimates for sensitivity, while very high estimates for specificity, something that will discuss at the later stage of this presentation. If we were to see now for the coxal index, again, we have the same image, the same output, with now that the optimal cutoff point for coxal index in nymphs is 1.2, while for adults is 0.9. So again, as expected, we get a lower threshold determination for the scrotal index where we go to the adults instead of the nymphs. Now, another thing that as part of the sensitivity analysis we had to consider, we considered some other scenarios. First of all, to explore the added value of the PCR when we want to determine the risk profile of a patient developing Lyme borreliosis. So at the first stage, we restricted to only PCR positive samples. So if you recall at the beginning, we had 44 individuals whose tick was tested positive to PCR. So we restricted, can run the same model only to these 44 individuals. And as expected, I'm showing the results for the scrotal index in nymphs. We had a decrease in the optimal threshold from 3.1 previously to 2.6. So I have the results restricting only to PCR positive samples to the left and the results from the main model on the right. However, the thing is that we only have 44 individuals. That is considered a small sample size. So you may see in the sensitivity here on the second figure on the left column that we have a high probability interval around the sensitivity. So the model does not produce the upside to that is that we have a high probability interval around the value that we have, that is the black line. And another thing that we want to explore is what would happen if we do not have the PCR at all. If we were to remove PCR from the equation and only have 3 tests, Scotland and Coxal index, and the clinical examination. No PCR information at all. And again, as expected, we have a very high increase in the optimal threshold for the Scotland index, that in this case is 4.7. So, regarding, however, the sensitivity and specificity estimates, we can see that in all the models, in all the scenarios, we get high estimates of the specificity, while the sensitivity is lower and ranging from higher values when we have only PCR positive samples, lowering when we have the main model, and even lower values of sensitivity when we exclude PCR from the equation at all. So if we were to summarize, you can see the image we have from Scotland index in NIMS when we are restricting all to PCR positive samples, when you can see that the cutoff value, that is the middle line, the middle vertical line, is 2.6, going to 3.1 when we are running the main model, when we have all the information both from clinical examination, Scotland and Coxal indices, and the PCR, and going to 4.7 when we exclude PCR from the equation. So, if we were to have some conclusions and some limitations of this study, I think that the added value of this approach is that, first of all, we assume the absence of a gold standard. So, all the tests in here are considered imperfect. So, there is always the space for a test not performing well. The other thing is, the other ultimate goal is that we have the evaluation of the Scotland and the Coxal indices at the range of the cutoff values. So, meaning that even though we estimate the sensitivity and specificity at the optimal cutoff value, we may choose, the clinician may choose to alter this threshold given the situations. Given, for example, disease context, you may have endemic versus non-endemic areas, and you may do that based on information you have available from other diagnostic methods. So, given the current context, a different cutoff value can be established. And also, what's another question that needs to be explained is what is the added value of a PCR. So, as we said, we can see how the threshold ranges when we only restrict to PCR positive or when we remove PCR from the equation. Lastly, the main limitation in this case is, as expected, that there are low prevalence rates of Lyme borreliosis in Serbia. As we said at the beginning, that there is a large number of tick-infested patients that will not develop disease. But because we only have around 3% in a way of the patient that will develop disease. So in a way, we are in a situation where we have very few positives, both to PCR and both to clinical examination. So in a way, the ability of the model to estimate sensitivity is very low. Because if you are saying that I have around 3% Lyme borreliosis at the patient level, so any positive that may come from the model, even if the model wants to say that this is a true positive, given that you are in a very low prevalence setting and that you have very few positives to clinical examinations and very few positives to PCR, these positives are treated to false positive by the model. So this is about why we have estimates of sensitivity around 20 and 25%. These are some key references for my study. I'd like to make some acknowledgements, first of all, to the Harmony Cost Action and to the Primary Cost Action for providing some funding via the short-term scientific mission to Addercam to develop this research. Of course, to my faculty and my supervisor, Professor Polchonis Kostoulas, and to the Pasteur Institute from Novi Sad, to Dr. Pavle Banovic. And I think I have some time left because this is a Bayesian method. We are happy that we are we are coordinating the Harmony Cost Action, and we have the Harmony Cost Action is closing to an end, and we are giving birth to the Society for Bayesian Methods in Epidemiology and Diagnostics, a Bayesian method like the one I discussed today, but also Bayesian methods and beyond Bayesian methods, and don't be afraid of the term Bayesian methods. And the aim of the society is to bring and to promote this type of approaches for life sciences. And we have the first conference of the Society 31 January and 2 of February. So if you're interested to attend the first conference of SBED, that is, you can use the scanner, the QR code to see some info, or you can find me around here also at the afternoon, the gala dinner, and we're happy to discuss more on that. And lastly, given Alejandro's info regarding artificial intelligence, I couldn't find a tick asking a question, so I asked ChatGPT-4 to draw me a tick, an Ixodes ricinus tick asking a question, and later on an Ixodes ricinus tick being very excited about Bayesian statistics. Thank you very much.